Uh, Bajpayee sir? Bajpayee sir is there?
Ram Prasad, hello, good morning.
Good morning, sir.
I think we should start. Let us not wait for one person.
Actually,
Let him join in the later stages.
I agree. I agree.
Okay.
We must always start on time.
Yes, and then he can join anytime. Maybe he is busy somewhere else.
Okay, okay, sir. Okay, sir. So I'm starting now.
Yeah,
So,
you should start.
Okay, so good morning to everyone. Today's chief guest and speaker of the webinar, world-renowned physicist Professor Ajoy Ghatak, distinguished professors, faculty members, scientists, researchers, and dear students. On behalf of Department of Pure and Applied Physics, Guru Ghasidas Central University, Bilaspur, and on my personal behalf, I, Dr. Ram Prasad Prajapati, welcomes you in the webinar on evolution of quantum mechanics by Professor Ajoy Ghatak. We are honored with the presence of our most respected and beloved Professor Ajoy Ghatak, sir. Sir, you hardly need any introduction. You have made all of us proud by your distinguished works in the field of optics and quantum mechanics. Professor Ghatak is more popular, especially in UG and PG level students, as and when they required help to understand the critical phenomena of quantum mechanics and optics. They often used to refer famous textbooks authored by him. My first meeting with Professor Ghatak was during the Duty Feast at IIT Delhi in 2017. At that time, I requested to Professor Ghatak for delivering a popular lecture at GGV through INSA lecture series, but somehow it could not become possible. So I am thank you, sir, for sparing your valuable time with us from your most busy schedule. In this webinar, nearly 950 participants were registered, and they are watching this webinar through the YouTube live and on Zoom also. So once again, I welcome you, sir, and let me call now Professor Ajoy Ghatak to deliver his most awaited webinar on evolution of quantum theory. Professor Ghatak, sir.
Thank you very much, Dr. Prajapati. Can you hear me? Can you hear me
sir.
clearly?
Yes,
can you
sir,
see? Can you see this first slide?
Yes, sir. We can see your slide.
Okay. Thank you very much, Dr. Prajapati. The title of my talk is actually "What is Light?" As you can see, I will first, for about half an hour or 20 minutes, I will talk on what is light, which led to the development of quantum theory. Okay. My teachers in quantum theory, I thought I should pay my respect to them. At Delhi University were Professor Daulat Singh Kothari and Professor Ramesh Chandra Majumdar, who taught us quantum mechanics and nuclear physics. And I was a student in Delhi University, MSc, doing my MSc during 1957 to 59. That is quite long time back. Here is a photograph of Dr. G.S. Kothari with me. And then this is Professor Ajit Ram Verma, another very distinguished physicist. I also had the great privilege of learning quantum mechanics from Professor Hans Bethe, Nobel laureate. At that time, he was not a Nobel laureate, who taught us 2 courses on quantum mechanics at Cornell University. I did my PhD at Cornell, and this was really a fabulous set of lectures, one on basic quantum mechanics and the other on intermediate quantum mechanics. He was a meticulous person, would write all the equations on the blackboard, as you can see. And it was really a great privilege to attend his classes. So these are my great teachers and who have initiated my interest in quantum mechanics. As you all know, the webinar is organized by Dr. Prajapati, and I'm very grateful to him. I think people like him are playing a very important role in promoting education in our country. And if time permits, I'm going to tell you the importance of education. We are a poor country, and the poverty can be removed only through education, science, and technology. I firmly believe that. अभी भी गरीबी तो बहुत है, और हमारे पास एक ऐसा माध्यम है, ये टेक्नोलॉजी है, जैसे वेबिनार्स है, जिससे गांव के लोगों को भी, कोई दूर गांव में भी इसका प्रचार हो सकता है, जो भी हम कहना चाहते हैं. So now with the advent of webinars and this fiber optic technology, we can educate masses. And so therefore I have always admiration for people like Dr. Prajapati who take the initiative for development of education. These are the classic books on quantum theory. First is by Dirac, Principles of Quantum Mechanics. These are the references for if you want to learn more on quantum mechanics. I'm sure all of you want to learn more on quantum mechanics. And someone wrote that Dirac's articles are like poems, but they do not contain figures. I mean, his book does not contain too many diagrams. And then you have the Feynman Lectures, Volume 3, which is a classic. And then you have the famous book, Quantum Theory by David Bohm. And then there is another book on quantum mechanics by Cohen Tanuji, which is translated by two of my very close friends, Nicole and Dan Ostrowski. I thought I should mention that both the Dirac, Feynman, and Cohen Tanuji are Nobel laureates. David Bohm is also a great physicist, was a great physicist, an equivalent to a Nobel laureate. तो ये एक बहुत सुंदर 1962 का एक फोटोग्राफ है, Feynman and Dirac talking physics, and both were great theoretical physicists. And David Bohm, you see, अगर आप ज़्यादा quantum theory पढ़ोगे, तो लोग कहते हैं कि you become a philosopher. And here is David Bohm talking spirituality to our spiritual guru, J. Krishnamurti. He became a spiritual person. This is Cohen Tanuji receiving the Nobel Prize. And this is Nicole and Dan Ostrowski in their home in Nice, in France. And I think that is me on the back. That was, I spent the summer there. Whatever I am going to do today, part of the optics is in my 7th edition, which is actually, I put in a lot of effort in preparing the latest edition, which should be out in a few weeks, I hope. तो सब कुछ, all intermediate कुछ mathematics तो एक घंटे के lecture में तो सब कुछ नहीं cover किया जा सकता है. So you have to fall back on this book. And then I have also written a book on quantum mechanics with Professor Lokanathan. उसका 6th edition और optics का 7th edition. तो इसमें भी कुछ दिया है. And for school students, I have written a book on 11th, 12th के student के लिए Einstein's Year of Miracles. 1905 was Einstein's Year of Miracles. चमत्कार का वर्ष 1905, 1905 में, जिस साल उन्होंने E is equal to mc square का आविष्कार किया, लाइट क्वांटम जिसको हम आजकल फोटोन कहते हैं उसका आविष्कार किया, और स्पेशल थ्योरी ऑफ रिलेटिविटी. तो इन तीन चीजों को किस तरह से एक स्कूल के 11वीं 12वीं के बच्चों को समझाया जा सकता है, इसका मैंने कोशिश किया है. तो ये किताब ये आप देख सकते हैं अगर आपकी इच्छा हो. तो एवर सिंस मैन कुड सी, जब से आदमी देख सकता है, उसकी यही इच्छा होती है कि ये लाइट, प्रकाश क्या है, व्हाट इज लाइट. ही हैज बीन वांटिंग टू नो, ही और शी. Here is a sadhu worshipping the light from the sun, and I'm sure he is also wanting to know what light is. So I'm going to try to answer that question. तो ये ऊपर वाला स्क्रीन नीचे आ रहा है, पता नहीं क्यों. So in Newton said, are not the rays of light very small bodies emitted from shining substances? So he put forward, as you know, the corpuscular model of light in his famous book on optics in 1687. Actually, the corpuscular model of light was first put forward by René Descartes, much before Newton. लेकिन न्यूटन का नाम इसलिए फेमस हो गया बिकॉज उनकी किताब जो है बहुत फेमस हो गई. इसीलिए the particle model of light, the corpuscular model of light is attributed to Isaac Newton. और इस particle model of light से उन्होंने स्नेल्स लॉ को डिराइव किया, तो लोगों ने सोचा कि particle model ही करेक्ट है. But light can propagate through vacuum, free space. जैसे sun और हमारे बीच में free space है, कुछ भी नहीं है. तो अगर light propagate करती है तो वो जरूर particle के रूप में होगी. Because a wave requires a medium. Sound waves require medium. अगर हमारे और आपके बीच में air नहीं हो तो वो sound नहीं reach कर पाएगी. So, because if light was indeed a bunch of particles, it should travel on straight lines and it should cast sharp shadows. परछाई जो है ना बिल्कुल, क्योंकि अगर डिफ्रैक्शन नहीं है तो परछाई बिल्कुल काला होना चाहिए. तो ये एक फोटोग्राफ है ऑफ द मैन ऑन द मून. तो चंद्रमा के ऊपर ये फोटोग्राफ है और देखिए ये आकाश पूरा नीला है, काला है. उसकी वजह ये है कि चांद में कोई एटमॉस्फेयर नहीं है, हवा नहीं है. तो ये जो आसमान नीला दिखता है वो स्कैटरिंग की वजह से दिखता है. अगर ये हवा नहीं हो तो आसमान बिल्कुल काला दिखेगा. और ये पृथ्वी है, दिस इज द अर्थ. And the shadows are completely dark, and therefore light almost travels in straight lines. लेकिन पृथ्वी के ऊपर अगर हम एक किताब पढ़ते हैं परछाई में, if I read a book in a shadow, then light does enter the shadow, and that is not due to diffraction. That is due to scattering of light by the air molecules. अगर हवा नहीं हो, if the air was not there, then you cannot read a book on your own shadow, as it is indeed the case on the surface of the moon. Then around 1650, around the same time as Newton, Christian Huygens put forward the wave theory of light. ये इनकी बहुत फेमस किताब है जो उन्होंने लिखी. उसका अंग्रेजी ट्रांसलेशन अब डोवर पब्लिकेशन ने छापा है. तो बहुत बढ़िया एक किताब लिखी थी जिसमें उन्होंने वेव थ्योरी ऑफ लाइट को पुट फॉरवर्ड किया. सो व्हाट इज ए वेव? द सिंपलेस्ट वेव इज, अगर आप एक स्ट्रिंग को टाइट करके पकड़ते हैं और उसको ऊपर नीचे करते हैं तो यू जनरेट, और मान लीजिए डिस्प्लेसमेंट जो है वो एक्स डायरेक्शन में है, so you generate an X-polarized wave. You propagate a disturbance. Each atom or molecule moves up and down, let us suppose, and the disturbance gets propagated from one place to the other. So this is the simplest wave, and the equation describing the X-polarized wave is given by this equation, as you all know. A is the amplitude, K is the wave number, omega is 2 pi times nu, and T is the time. तो किसी तरह से अगर ये इक्वेशन आपके पास आ जाता है तो आप प्रेडिक्ट कर सकते हैं कि वेव जरूर होगा, जैसे मैं आपको बताऊंगा। तो इसको यूजुअली यू राइट इट एज रियल पार्ट ऑफ e to the power of I k z minus k omega t. So why does this equation represent a wave? आप किस तरह से साबित कर सकते हैं कि ये इक्वेशन एक वेव को रिप्रेजेंट करता है? तो देखिए, इसमें से हमने k को बाहर निकाल लिया, तो आई राइट दिस एज z minus vt, where v is defined to be equal to omega by k. यहाँ पर 3 इक्वल टू साइन होनी चाहिए थी. That is, v is defined to be equal to omega by k. और मैं आपको ये प्रूव करूंगा that v represents the velocity of the wave. Because इसको मान लीजिए t equal to 0 पर a cos kz है, यहाँ पर t equal to 0 लगा दिया, और at a slightly later time the whole curve shifts by a distance v delta t in the positive z direction. So therefore, this is the snapshot of the string at t equal to 0. और थोड़ी देर बाद the displacement moves by a distance v delta t in the plus z direction. So therefore, this equation x sub z is equal to a cos kz minus omega t represents a wave propagating in the plus z direction with velocity v, where v is defined to be equal to omega by k. ठीक है? And k is equal to 2 pi by lambda. ये तो सब आजकल हाई स्कूल में पढ़ा देते हैं. तो एक मान लीजिए काम पूल ऑफ वाटर है, और वहां पर मैंने एक शार्प पेंसिल को ऊपर नीचे ऑसिलेट किया, so it generates circular waves. The water molecules do not go outwards, but it transfers the energy from one place to the other. That is the definition of a wave. तो देखिए यहाँ पर 2 point sources and each on a ripple tank, let us suppose S1 and S2, and you have 2 point sources oscillating up and down, each generating a water wave. If one produces a displacement like this, a cos omega t, and the other produces a displacement minus a cos omega t, then they interfere and produce a zero displacement. And therefore, that is a node. If one produces a displacement a cos omega t, and the other also produces a displacement a cos omega t, then the displacements are said to be in phase, and you get a maximum intensity. So this is an actual interference pattern produced from 2 point sources vibrating in phase in a ripple tank. And you can see the formation of interference fringes. So if light was a wave, it should produce an interference pattern. लेकिन इंटरफेरेंस पैटर्न अगर आप 2 लाइट्स को ऑन कर दें तो वो नहीं दिखता है. It requires a careful setup. It was only in 1801. तो आप ध्यान दीजिए that 17th century में हाइगेंस ने वेव थ्योरी को propound किया. Or it was only early 19th century that a British medical doctor, Thomas Young, carried out the 2-hole experiment. ये जो Thomas Young का experiment है, the original experiment is not a double slit experiment. It's a double hole experiment. 2 tiny holes छेद करके एक screen में sunlight was allowed to fall. It was passed through a filter, And then on the screen, he obtained interference pattern. And the fringe width, the distance between two white and bright fringes, that is beta. D is the distance between the two holes, small d. And capital D is the distance between this, and that is equal to the wavelength. So he could calculate the wavelength. आप ध्यान दीजिए कि if you have two tiny holes, you will get straight line interference pattern. So you do not require two slits. And in fact, the original experiment of Thomas Young, which is described in Dennis Gabor's Nobel lecture, consisted of two holes. और उसी से straight line interference fringes आती है. ये diagram हमने Feynman lecture से लिया है. It is from the Feynman lectures. If you have particles like gun emitting tiny bullets, and you do the double hole experiment, if hole number 1 is open, you get, and it is a detector here on the screen, you get an intensity distribution like this. If you hole number 2 is open, you get an intensity distribution like this. अगर दोनों hole open हो, if both holes are open, then you get P12, which is P1 plus P2. That is, either the bullets will pass through hole number 1 or hole number 2. जैसे आपने tiny particles भेजे, तो वो या तो hole number 1 से जाएगा या hole number 2 से जाएगा. तो इसलिए you will not observe any interference pattern, and you obtain the total intensity pattern as P1 plus P2. लेकिन अगर आपके पास वेव सोर्स है, जैसे मैंने आपको अभी बताया, तो दो होल से वेव्स एमिनेट करेंगे और वो इंटरफियर करेंगे. तो I1 is the intensity distribution when hole number 1 is open. I2 is the intensity distribution when hole number 2 is open. और जब दोनों होंगे तो जैसे मैंने आपको अभी समझाया, उससे इंटरफेरेंस पैटर्न होगा और उसमें मैक्सिमम एंड मिनिमम इंटेंसिटी होगी. And this interference pattern is because of the superposition principle associated with the wave phenomenon. So when Thomas Young carried out this experiment, he could say light plus light could produce darkness. तो एक स्क्रीन में एक ऐसी जगह, बहुत सारी ऐसी जगह है, एक होल ओपन है तब लाइट है, दूसरा होल ओपन है तो लाइट है. अगर दोनों होल ओपन है तो वहां पर डार्कनेस है. तो वो तभी हो सकता है जब लाइट एक वेव फिनोमेना. तो ये this beautiful experiment of Thomas Young established without doubt the wave nature of light, and the wavelength was found to be about half of a micron. And because the wavelength is very small, half of a micron means half of a millionth of a meter. And so therefore, it is difficult to carry out the experiment. लेकिन आप लोगों ने तो सबने फ्रेनेल बाइप्रिज्म का एक्सपेरिमेंट किया ही होगा और उसके इतने ब्यूटीफुल इंटरफेरेंस फ्रिंजेस देखे होंगे. एक एंड्रू रॉबिन्सन ने एक किताब लिखी है अबाउट थॉमस यंग, द लास्ट मैन हु न्यू एवरीथिंग. द लास्ट मैन, ही वाज अ ग्रेट medical doctor, great physicist, he knew everything. That's what people say. You know, if you talk about physics, then people say that the Russian physicist Landau and the American physicist Richard Feynman, they knew entire physics. They were the last people who knew entire physics. अब physics तो इतना विशाल सब्जेक्ट हो गया है कि कोई भी हर एस्पेक्ट को जान नहीं सकता. So light was a wave, but how could it propagate through vacuum? ये तो सूरज से हमारे पास जो रोशनी आती है, तो वो वैक्यूम फ्री स्पेस से ट्रैवल करती है. If it was indeed a wave, then how could it propagate through vacuum? That was the main question that was being asked, and the ether theory was developed. The ether does not exist. Ether is a substance which is present even in vacuum. Now we know that ether does not exist. इसलिए हम उसको और बात नहीं करेंगे. तो 19th century में, जैसे आप लोगों को सबको मालूम है, laws of electricity and magnetism were getting discovered. फैराडे ने डिस्कवर किया कि अगर कोई मैग्नेट को आप ऊपर नीचे करते हैं तो कॉइल में करंट आ जाता है. A changing magnetic field produces a current, and he put forward a law which Maxwell put forward in the form of an equation, that curl of E is equal to minus delta B. This is one of Maxwell's equations. उस वक्त एम्पियर ने भी एक लॉ बताया जिसमें मान लीजिए एक कंडक्टर है, करंट कैरी कर रहा है, इट प्रोड्यूसेस ए मैग्नेटिक फील्ड. तो मैक्सवेल ने इस लॉ को वेक्टर फॉर्म में लिखा और कहा कि एम्पियर लॉ is curl of H is equal to J, where J is the current density and H is the magnetic field. But Maxwell did one more thing. That was a great contribution of Maxwell. He said not only a current can produce a magnetic field, but a changing electric field can also produce. So this is known, as you must be knowing, as displacement current. तो मैक्सवेल ने एम्पियर्स लॉ में एक और टर्म ऐड कर दिया और वो टर्म है द कॉन्सेप्ट ऑफ, आप लोग सब अपना माइक बंद करके रखिएगा क्योंकि आप लोग बात करते हैं तो वो आवाज आ जाती है. काइंडली स्विच ऑफ योर माइक, ऑल ऑफ यू. So this is the concept of displacement current, that not only a current, ordinary current can produce a magnetic field, but a changing electric field, like between the plates of a condenser, they can also produce a magnetic field. So plates of a condenser पर अगर changing electric field होगा तो उससे भी magnetic field generate होगा. Now let us suppose you take Faraday's law. इसको ध्यान से देखिए. Faraday's law में हमने एक wave like expression for the electric field को substitute किया. So I assume an X polarized wave for the electric field. और ये equation जो है जैसे मैंने आपको बताया, this represents a wave. इसका कर्ल निकाला और फिर इसको इंटीग्रेट कर दिया तो हमारे पास ये एक्सप्रेशन आएगा. दिस आई लीव फॉर द स्टूडेंट्स, आई एम टॉकिंग ओनली टू द स्टूडेंट्स. इसको this is left as an exercise. You can show that if you assume this expression for the electric field, then the corresponding magnetic field is given by this. So they are in phase. And then I take both these equations and I substitute in this modified form of Ampere's law in free space. Free space में वो J 0 है, तो free space में Ampere's law becomes like this. तो इन दोनों equations को अगर मैंने इस equation पर substitute किया, तो then I can show that omega by k comes out to be this. And if you substitute the values of mu naught and epsilon naught, then you get a value about 300 million meters per second. So therefore, understand what Maxwell did. He wrote the laws of electricity and magnetism in the form of vector equation, and he showed that wave-like expressions are solutions of Maxwell's equations, and therefore he predicted the existence of electromagnetic waves. That is the most important thing. He predicted the existence of electromagnetic waves, और उन्होंने ये भी प्रेडिक्ट किया कि इलेक्ट्रोमैग्नेटिक वेव्स की जो वेलोसिटी होगी वो 300 मिलियन मीटर्स पर सेकेंड होगी इन फ्री स्पेस. So physically, a changing electric field will produce a changing magnetic field. A changing magnetic field will produce a changing electric field. And that is what is propagated in free space. That is the electromagnetic wave. The concept of the field was introduced by Michael Faraday, जिसको हम लोग आजकल we take for granted. उन्होंने ये कहा फैराडे ने कि एक चार्ज जो है उसके पहले क्या था, एक चार्ज दूसरे चार्ज को either there is a force of attraction or a force of repulsion. But what Faraday said was that this charge produces a field. और वो field हर जगह पर present है, even in vacuum. और जब वहां पर किसी और स्थान पर आप एक चार्ज को रख देते हैं तो उसमें या तो फोर्स ऑफ अट्रैक्शन होता है या फोर्स ऑफ रिपल्शन होता है. So the concept of the field was introduced by Michael Faraday. So therefore, these are the, in free space, these are the Maxwell's equations, these are the laws of electricity and magnetism. You know, Maxwell wrote down 4 equations. These are known as Maxwell's equations, which cannot be derived. They are based on experimental laws. And the entire field of classical electricity and magnetism are just solutions of Maxwell's equations under different boundary conditions. ये मैंने एक बहुत important बात कही, ध्यान से सुनिए. The entire field of classical electricity and magnetism are just solutions of the 4 Maxwell's equations under different boundary conditions. And if you write the Maxwell's equations in free space, they admit solutions of a wave-like form, whose velocity in free space is about 300 million meters per second. अगर इलेक्ट्रिक फील्ड 0 होगा तो मैग्नेटिक फील्ड भी 0 होगा, और मैग्नेटिक फील्ड 0 होगा तो इलेक्ट्रिक फील्ड. So none can exist without the other. And that is the concept of the electric and magnetic fields, wave-like solutions for the electric and magnetic. लेकिन जो मैक्सवेल ने जो डिस्कवर किया, उसने कहा कि not only that electromagnetic waves exist, लेकिन उसका जो velocity है वो इतना होना चाहिए. लेकिन ये जो नंबर है, उस वक्त फिजो ने लाइट की वेलोसिटी मेजर की थी, वो भी करीब 300 मिलियन मीटर्स पर सेकेंड था. तो उन्होंने कहा कि ये 2 नंबर जो हैं करीब करीब बराबर है. And then he said light must be an electromagnetic wave. This is said to be one of the greatest syntheses in the development of science. This is said, एक सब्जेक्ट है ऑप्टिक्स और एक सब्जेक्ट है इलेक्ट्रिसिटी एंड मैग्नेटिज्म. दोनों को उन्होंने सिंथेसाइज कर दिया कि all of them, the entire field of optics and the entire field of electricity and magnetism are just solutions of Maxwell's equations. This was one of the greatest syntheses in the history of development of science. So he said, around 1864, he wrote this beautiful book on treatise on electricity and magnetism, and he predicted the existence of electromagnetic waves. He predicted them and said light itself is an electromagnetic wave. And one could say that God said, let there be Maxwell's equations, and there was light. Okay. 1887 में हाइनरिक हर्ट्ज ने इलेक्ट्रोमैग्नेटिक वेव्स को जनरेट किया, एक एल्यूमिनियम फॉइल से रिफ्लेक्ट करके स्टैंडिंग वेव्स जनरेट किया. He could calculate the wavelength and the frequency, and he found that the velocity of these electromagnetic waves was around 300 million meters per second. So after Heinrich Hertz's experiment in 1887, electromagnetic waves were greatly established. It could explain everything, reflection and refraction of light, etc., etc., etc. तो मैं आपको एक एक्सपेरिमेंट बताता हूँ. एक ग्लास प्रिज्म है और लाइट आ रही है, मान लीजिए एक रेड लेजर बीम है, एंड इट अंडरगोस टोटल इंटरनल रिफ्लेक्शन. ये एंगल जो है क्रिटिकल एंगल से ज्यादा है. और एक दूसरा प्रिज्म लगा दिया, लेकिन बीच में एक एयर गैप है. तो इससे क्या हो जाता है, थोड़ी सी एनर्जी टनल कर जाती है. दिस इज नोन एज ऑप्टिकल टनलिंग. इट्स ए क्लासिकल experiment, classical physics, classical electromagnetic theory. This is known as FTIR, frustrated total internal reflection. And it was Jagadish Chandra Bose, the Indian physicist, around 1894. You must remember, Heinrich Hertz did his experiment in 1887. And Jagadish Chandra Bose did this optical tunneling experiment. These are the actual prisms that he used to demonstrate optical tunneling using millimeter waves. He was the first to demonstrate optical tunneling using millimeter waves. विदेशी किताबों में इसका जिक्र ज्यादा नहीं करते हैं, तो मैंने सोचा कि आप लोगों को बता दें. So this is the entire spectrum of electromagnetic waves, from gamma rays that are generated in nuclear reactions, to X-rays, to ultraviolet, to the visible region of the spectrum, infrared, जो आपके माइक्रोवेव ओवन है उसमें जो रेडिएशन है, और जो रेडियो वेव्स है जो आपके मोबाइल फोन पर आती हैं, they are all electromagnetic waves. They all belong to different wavelengths or different frequencies. Gamma rays are very high frequencies, as you all know. The visible region has a frequency around 10 to the power of 15 hertz. The wavelength is about 0.5 micron. And the visible region of the spectrum, from blue light to red light, occupies a tiny portion of the entire electromagnetic spectrum. But all wavelengths travel with an identical velocity of 299,792,458 meters per second. So Max Planck had said, Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. Greatest triumphs. In fact, Maxwell's electromagnetic theory explained everything. Solid state physics कहो, मतलब reflection, refraction, total internal reflection, सब कुछ explain कर दिया. So Lord Kelvin ने कहा, there is nothing new to be discovered in physics now. 1894. All that remains is more and more precise measurement. Then 1905 में, जैसे मैंने आपको पहले कहा था, that is known as Einstein's year of miracles. Annus mirabilis. Annus mirabilis are Latin words meaning year of miracles. In the second paper in his year of miracles, Einstein wrote, radiation energy, light, consists of indivisible quanta of energy. He predicted the existence of photons, and the energy of the photon is equal to h nu. He called them quanta of energy, which were later named as photons. And that in a later paper, he said that the momentum of the photon is given by h nu by c, where h is the Planck's constant, nu is the frequency, and c is the velocity of light in free space. He explained, as you all know, the photoelectric effect. And he said that when light is incident on a metal surface like sodium or potassium or cesium, then electrons are emitted. And the maximum kinetic energy of the electron is given by this equation. This is known as Einstein equation. And it is for this equation that he was awarded the Nobel Prize. Not for his theory of relativity, even for his general theory of relativity, not even for the concept of the light quantum. No one believed that. Because at that time, Maxwell's electromagnetic theory was so well established that it was not believed. This equation was very carefully verified by Robert Millikan, and he calculated the maximum kinetic energy of the emitted electrons, and he found that to fit very well with the equation that was predicted by Albert Einstein. Albert Einstein received the 1921 Nobel Prize in physics for the Einstein equation, which was verified by Robert Millikan, and who received the 1923 Nobel Prize in physics. Then came Compton. After Einstein received the Nobel Prize, Arthur Compton did very beautiful experiments in which a high energy photon of a very large frequency, a gamma ray photon, hits an electron and gets scattered. It's an elastic collision. The frequency becomes smaller, and then it imparts a certain energy to electron. Just by using conservation laws, he could calculate the frequency or the wavelength of the scattered radiation as a function of the scattering angle. And this is his theoretical prediction, assuming that the energy of the light quantum or the energy of the photon is equal to h nu, and the momentum of the photon is h nu by c. And it agreed very well with experiments. Dr. Prajapati, बहुत लोग disappear हो रहे हैं अभी तो 228 participants. I hope.
Actually, sir, many students they are watching on YouTube live around 350.
अच्छा ठीक है मैंने सोचा कि शायद उनका
No. Students they are watching on YouTube live.
यही तो वेबिनार का एक बहुत बड़ा प्रॉब्लम है कि वो स्टूडेंट भाग जाते हैं कि सो गए हैं, इसमें पता नहीं चलता.
No, sir. We are getting a excellent response from the participants.
चलो. Thank you. So it was only after Compton did this very beautiful experiment that people started believing in Einstein's light quantum. So Einstein's light quantum, ध्यान दीजिए, was put forward in 1905, but people started believing in the photon concept, that is the wave-particle duality. Who discovered wave-particle duality? Albert Einstein, because he said that light also has a particle nature of radiation. And it was only after Arthur Compton's experiment that people started believing in the concept of the photon. And Compton, as you all know, received the 1927 Nobel Prize in Physics for his discovery of what we now call as Compton scattering. Then J.J. Thomson in 1897 discovered the electron. Electron को एक electric field से its trajectory can be changed. We now know the mass to 10 decimal places. We know the charge of the electron to 10 decimal places. So it can be deflected by an electric or a magnetic field. And so therefore, on the back of our mind, we feel that it's a tiny particle. एक छोटा सा particle है जिसको हम इधर उधर deflect करके कर सकते हैं. So the particle nature of electron was put forward by J.J. Thomson in 1896. He discovered the electron, for which he was awarded the 1906 Nobel Prize in Physics. Then Louis de Broglie in 1924 said that जैसे photon के लिए Einstein ने कहा है P is equal to h nu by c. So this is h by lambda. So this relation is also should be valid for electrons. उन्होंने predict किया. That is the beauty of theoretical physics. उन्होंने predict किया कि electron भी wave-like behavior exhibit करना चाहिए. देखिए, how did he predict that? He said, जैसे आप लोगों ने बोर्स मॉडल तो पढ़ा होगा, 1913 में नील्स बोर ने कहा कि he gave a theory for the hydrogen atom, and he said that each discrete orbit corresponds to a discrete value of the angular momentum. MVR is equal to n is 1, 2, 3 multiplied by h by 2 pi. So this means Louis de Broglie said 2 pi r is equal to nh by mv. So that is nh by p. So he said that each discrete Bohr orbit consists of something like a stationary wave. And so therefore the electron must exhibit wave-like properties, and the wavelength should be given by h by p. ये उन्होंने 1924 में predict किया. That was his PhD thesis. अच्छा, नील्स बोर दिल्ली यूनिवर्सिटी में 1960 में आए थे, 60 साल पहले. So I was a young man at that time. I just had passed out my MSc. That is me. This is Professor R.P. Mitra. That is Niels Bohr. This is Professor F.C. Euler. कुछ लोगों ने उनका नाम सुना. So Niels Bohr received the 1922 Nobel Prize in Physics for his theory of the hydrogen atom. And Louis de Broglie received the 1929 Nobel Prize in Physics for his discovery of wave nature of electrons. So जरा ध्यान दीजिए, who discovered wave-particle duality? Wave-particle duality was discovered by Albert Einstein, because at that time the wave theory of light was established, the electromagnetic wave was established. He said it must also exhibit particle nature. Then de Broglie said that because light has a dual nature, electron must also demonstrate. He predicted that in 1924. And only in 1926 or 27, the wave nature of electrons was experimentally established after the prediction of Louis de Broglie. And the beautiful experiments were carried out by Davison and Germer and G.P. Thomson, son of J.J. Thomson. J.J. Thomson discovered the electron, and G.P. Thomson discovered the wave nature of the electron. And this is the diffraction pattern and produced by X-rays of aluminum foil. X-rays fall on aluminum foil and they produce this diffraction pattern. And electrons fall, they also produce a very similar diffraction pattern. So जो भी है, इलेक्ट्रॉन और लाइट दोनों एक ही है. अगर दोनों पार्टिकल हैं, दोनों वेव हैं, जो भी है, they are both similar. So Davison and Thomson shared the 1937 Nobel Prize in Physics, And Germer, who was also a collaborator, missed out on the Nobel Prize. Now, इसको ध्यान से सुनिए. So therefore, the electron or a proton or a photon or a neutron, is it a wave or a particle? तो आप किताबों में पढ़ेंगे कि वो कोई किताब लिखता है कभी वेव है कभी पार्टिकल है, कोई लिखता है वेव भी है पार्टिकल भी है, and it sometimes behaves like a wave, sometimes behaves like a particle. Those are not the correct answers. The correct answer is that it is neither a wave nor a particle. इसको जरा ध्यान से सुनिए कि ये neither, ये wave भी नहीं है particle भी नहीं है. और ये किसने कहा? ये कहा फाइनमैन. और मैं फाइनमैन को इसलिए कोट करना चाहता हूँ क्योंकि मैं अगर कहूँगा तो आप लोग विश्वास नहीं करेंगे. तो फाइनमैन लिखता है अपने फाइनमैन लेक्चर्स में, ध्यान से सुनिए, they are neither waves nor particles. So therefore, वो है क्या चीज? The quantum theory says that the electron or proton, if you ask me, what is an electron? The correct answer is, I don't know. It is described by a wave function psi. What is this wave function psi? It is the solution of the Schrödinger equation. ये आपने कैसे लिख दिया? You will ask me. So the answer to that question is, again, I quote Feynman. और इसको ध्यान से सुनिए. Where did we get that equation from? Feynman says, nowhere. It is not possible to derive it from anything you know. इस equation को आप derive नहीं कर सकते हैं. It came out of the mind of Schrödinger. तो जरा इस पर गौर करिए. The most important point that I have tried to make is that the electron or the proton or the neutron is neither a particle nor a wave. और इसका मैं experimental proof दूंगा. तो फिर है क्या चीज? You cannot physically understand that. It is described by the wave function psi, which is the solution of the Schrödinger equation. And the Schrödinger equation cannot be derived. It came from the mind of Schrödinger. Schrödinger also had a very, it is so beautiful, and people love this equation so much that they paint the equation on them. अगर आप गूगल में जाएंगे, इंटरनेट में जाएंगे और कहीं पेंटेड श्रोडिंगर इक्वेशन, तो लोग अपने पीठ पर, अपने मुंह पर श्रोडिंगर इक्वेशन को टैटू करके. I will give you a heuristic derivation. जो this is one of the many derivation. हर किताब में जो श्रोडिंगर इक्वेशन का डेरिवेशन है, it's a very heuristic argument. किसी तरह से श्रोडिंगर इक्वेशन पर अराइव करें. अगर आप 1926 का श्रोडिंगर का पेपर देखेंगे, उसमें अलग सा एक डेरिवेशन, क्योंकि उसको डिराइव नहीं कर सकते हैं फ्रॉम क्लासिकल फिजिक्स. तो देखिए, जैसे मैंने आपको पहले कहा था, एक प्लेन वेव इज डिस्क्राइब्ड बाय दिस. इसमें किसी तरह से मैं वेव पार्टिकल डुअलिटी को इंजेक्ट करना चाहता हूं. तो वी हैव द डी ब्रॉगली रिलेशन, P is equal to h by lambda, 2 pi से multiply और divide किया. So this is h cross and this is k. So k is equal to P by h cross and h cross is equal to h by 2. We also have the Einstein relation. E is equal to h nu. So this is equal to h cross omega. So omega is equal to E by h cross. तो इसको मैंने यहाँ पर डाला. K की जगह P by h cross और ओमेगा की जगह E by h cross लगा दिया. तो ये आ. So we will say that approximately, that intuitively, the function, the wave describing the electron will be something like this, where for a free particle, E is equal to p square by 2m. Let us suppose I have a free non-relativistic particle. I have a free non-relativistic electron. So then I have psi of xt is equal to I by h cross px minus et. ये तो मैंने अभी derive किया था. Heuristic derivation. इसमें कोई ज़्यादा rigor नहीं है. किसी तरह से I want to arrive in. And then for a non-relativistic particle p square by 2m, तो इसको मैंने e को replace कर दिया p square by 2m. अच्छा, इसको एक दफे टाइम के with respect to differentiate किया. So I get delta psi by delta t. आ गया p square by 2m. I h cross से multiply कर दिया तो I square is -1 minus minus plus h cross h square. तो ये और इसको दो दफे x से differentiate कर दिया तो आ जाएगा I by h cross p whole square, that is minus h cross square p square by h cross square कट गया तो ये आपका. तो और उसको मल्टीप्लाई कर दिया दो दफे डिफरेंशिएट करके उसको माइनस एच क्रॉस स्क्वायर बाय 2m से मल्टीप्लाई कर दिया. इसको आप लिख लीजिए. तो ये p स्क्वायर बाय 2m टाइप्स है. तो राइट हैंड साइड से बराबर है इसलिए मैंने लेफ्ट हैंड साइड को बराबर कर दिया. सो आई हैव डिराइव्ड दिस. अब ये मेरा दिस इज द so I forget the derivation which lacks rigor. I forget the derivation and I take this as my truth. यही परम सत्य है. अगर हम वन डायमेंशनल वेव की जगह 3 डायमेंशनल वेव लेते तो ये 3 डायमेंशनल श्रोडिंगर इक्वेशन. ये तो आप किसी भी किताब में, हमारी किताब में या किसी भी किताब में आप देख सकते हैं. So I now go back, I forget the derivation and I say that the electron is described by the wave function psi, which is the solution of this equation. And I tell you, tell the students, that don't ask me how I have derived this equation. तो इसको by method of separation of variables बस इसी से शुरू करते. This is the starting point. प्रजापति जी टाइम क्या हो गया? वो 11:30.
Sir, it is 11:30.
अच्छा, तो थोड़ा सा और कर लेता हूँ. Then
No problem, sir. You can continue.
ये देखिए ना, मैं चाय का भी चाय का बंदोबस्त तो आपको करना चाहिए था.
Actually, sir, we can't do anything, sir.
I know,
But
I know.
it will be due, sir. When the situation will come normal, you are more invited here.
तो इसका now I hope you are understanding what I am trying to say. I start with this equation. Quantum mechanics starts with Schrodinger equation, non-relativistic equation. And now I play around with solutions. आप ध्यान दीजिए, एक चीज मैं बताना चाहता हूं, इसको जरा ध्यान से सुनिए. The entire electricity and magnetism, classical electric, are solutions of Maxwell's equations, which are experimental laws, cannot be derived. Entire electricity and magnetism are solutions of Maxwell's equations, which are experimental laws, cannot be derived. Similarly, the entire non-relativistic quantum mechanics, जो आप लोग BSc ऑनर्स में या MSc में पढ़ते हैं, it's just the solution of Schrodinger equation, जो मैंने लिखा है. इसमें स्पिन ऑफ द इलेक्ट्रॉन को अलग से जोड़ दिया जाता है. That spin has that the electron or the proton has a tiny magnetic moment. What is the spin? The spin, I associate an electron with a tiny magnet. उसका एक magnetic moment है. वो मैं किसी दिन और बताऊंगा. So the entire non-relativistic quantum mechanics, a major portion, I should say major portion, is just the solution of this equation. And this equation cannot be derived. इसको आप derive नहीं कर सकते हैं rigorously. ये कहाँ से आया? श्रोडिंगर के दिमाग से आया, हाइजेनबर्ग के दिमाग से आया. तो देखिए, now I then start quantum mechanics. I start electricity and magnetism with Maxwell's equations. Similarly, इसीलिए मैंने Maxwell equation को थोड़ा सा time दिया है. Similarly, quantum mechanics I start with Schrodinger equation. और फिर इसको मैंने सॉल्व करना शुरू किया. और जब मैं सॉल्व करता हूं तो ये आएगा. इसी को लेकर के तो मैंने ये इक्वेशन डिराइव किया है. बट उसको मैं भूल जाता हूं. इसको मैं सॉल्व करने की कोशिश करता हूं. अगर आप इसको सॉल्व करेंगे by using the method of separation of variables, I will get this, where p can go from minus infinity to plus infinity and should be real. Since p can take any value, I am now talking of a free particle. So v is 0, potential is 0. Since p can take any value from minus infinity to plus infinity, so the most general solution is the superposition. लेकिन एक डिफरेंशियल इक्वेशन का अगर सोल्यूशन sin ओमेगा t है और cos ओमेगा t है, तो जनरल सोल्यूशन क्या होगा? a sin ओमेगा t प्लस b cos ओमेगा t. अब मैं कह रहा हूं कि ये सोल्यूशन है इस इक्वेशन का, where p can take any value from minus in, तो उसका एक सुपरपोजिशन जो होगा, since p takes a continuous variation, तो उसका सोल्यूशन a free electron is described by this equation. This is known as a wave packet. और ये जो मैंने 2 pi h cross लगा रखा है, ये just for the sake of convenience. ध्यान से सुनिए. So in 1926, Max Born Schrodinger equation was discovered in 1926. Max Born ने इसका physical interpretation दिया. It's a distribution. Psi square is not probability. बहुत किताबों में लिखा है. Is the probability. Is psi square dx is the probability of finding the electron between x and x plus dx. तो इसीलिए psi square जो है, उसका dimension inverse length का होता है. Because जब हम इसको dx से multiply करते, इसीलिए this is not an ordinary function. This is known as a distribution. Is the probability of finding the electron between x and x plus dx. And he also showed that a of p squared dp is the probability of finding the x component of the momentum of the electron between p and p plus dp. देखिए, मैं थोड़ा सा example देता हूँ. The Max Born received the half of the 1954 Nobel Prize in Physics. तो मान लीजिए, देखिए, psi of x, 0, हम एक इलेक्ट्रॉन को प्रिपेयर करते हैं, मान लीजिए फिलामेंट से निकलता है. It is described by this wave function. ये जो फैक्टर है, ये तो this is p of x dx is equal to mod psi x dx is equal to so much. इसको अगर हम इंटीग्रेट करेंगे from minus infinity to plus infinity, वो 1 आ जाएगा. इसको अगर हम इंटीग्रेट करेंगे from minus infinity to plus infinity, तो 1 आ जाएगा. इसी से ये फैक्टर दिया गया. Then I just wrote down that this is the general, this is equation describing a wave packet. तो देखिए, t को 0 रख देते हैं. तो t को 0, तो ये 0 हो गया, p square by 2m times t, ये 0 हो गया. ये तो this is a Fourier transform relation. इसी दिन मैं आप लोगों को Fourier transform अच्छी तरह से समझा दूंगा. Psi of x, 0 is so much. इसका अगर आप universe Fourier, if psi of x 0 is so much, then a of p is the inverse Fourier transform. यहाँ पर प्लस साइन है, यहाँ पर माइनस साइन. तो देखिए, अगर मुझे psi of x, 0 मालूम है, तो a of p psi of x, 0 पर इसको सब्स्टिट्यूट करके a of p निकाल देंगे. a of p अगर मालूम है, तो इसमें सब्स्टिट्यूट कर लेंगे और फिर इंटीग्रेट कर लेंगे, तो हमको टाइम एवोल्यूशन ऑफ द वेव पैकेट आ जाएगा। दोबारा सुनिए। सो फ्रॉम दिस इक्वेशन आई गेट psi of x, 0 is so much, यहाँ पर 0 कर दिया तो ये, एंड देन इसका मैंने इनवर्स फूरियर ट्रांसफॉर्म लिया। ये मैंने ऑप्टिक्स की किताब में भी और क्वांटम मैकेनिक्स की किताब बहुत अच्छी तरह से समझाने की कोशिश की है। देन a of p is given by this। अगर psi of x, 0 मालूम है तो मैं a of p को यहां से निकालूंगा, एंड a of p को यहां पर सब्स्टिट्यूट करके देन आई इंटीग्रेट इट and I can get the time evolution of the wave packet। तो अगर मान लीजिए psi of x, 0 ये है, तो a of p निकालने के लिए मैंने इसको यहाँ पर सब्स्टिट्यूट किया। इट विल रिक्वायर, ये आप लोग करिएगा, तो a of p स्क्वायर को कैलकुलेट कर सकते हैं and you will get this। So the probability that the particle lies between x and x plus dx is given by this, and the probability that the momentum lies between px and px plus dx is given by this। So if the particle is localized at x is equal to 0 and delta x, this is the Gaussian distribution. So the corresponding momentum distribution function, this is known as the position distribution function, psi of x, 0 mod square. This represents, it's a distribution, position distribution function। अगर कोई पार्टिकल सिग्मा नॉट, या if it is localized within sigma naught, then it is, its momentum distribution is localized within h cross by sigma। So therefore uncertainty principle is contained in the solution of the Schrodinger equation। ये ध्यान दीजिए, uncertainty principle ऊपर से नहीं है, हर solution Schrodinger equation का contains the uncertainty principle। ये जो मैंने आपको पहले कहा था कि अगर मुझे psi of x, 0 मालूम है तो a of p मैं निकाल सकता हूं इस इंटीग्रेट को एवेल्युएट करके, a of p कैलकुलेट करके यहां पर लगा दिया तो मैं टाइम एवोल्यूशन ऑफ द वेव फंक्शन कर सकता हूं। सो दिस इज द टाइम एवोल्यूशन ऑफ द वेव पैकेट। सो इलेक्ट्रॉन इज डिस्क्राइब्ड। सो व्हाट इज एन इलेक्ट्रॉन? इज इट ए वेव और ए पार्टिकल? द आंसर इज इट इज नाइदर। ना ये पार्टिकल है ना ये वेव है, इसको आप ध्यान से सुन लीजिए। But if it is localized with its, I describe it with a wave function, which is something like a wave packet। और जब ये t equal to 0 पर अगर यहां पर localized है, t equal to t0 पर यहां पर localized होगा, तो it moves with a certain group velocity। इसको आप करिएगा, इंटरमीडिएट स्टेप्स वर्कआउट करिएगा कि इस तरह से प्रोपोगेट कर रहा है। दिस इज द रियल पार्ट ऑफ psi of x, t। ये मेरे खुद के कैलकुलेशंस। मान लीजिए ना, इसको ध्यान से सुनिए, एक पोटेंशियल बैरियर पे वेव पैकेट आता है, मतलब एक इलेक्ट्रॉन सीज ए पोटेंशियल बैरियर। ध्यान से सुनिए, आप लोगों ने, बहुतों ने किया होगा एक टनलिंग थ्रू ए बैरियर, तो उसका एक रिफ्लेक्शन कोफिशिएंट भी है, ट्रांसमिशन कोफिशिएंट। तो अगर आप वेव पैकेट को इंसिडेंट करते हैं at t equal to 0, let us suppose it is localized here, ये इलेक्ट्रॉन इधर से आ रहा है, और जब इसको सॉल्व करते हैं इसका रिफ्लेक्शन कोफिशिएंट भी है और इसका ट्रांसमिशन कोफिशिएंट भी है। So this is the reflected wave packet and the transmitted wave packet। Now ध्यान से सुनिए, ये जो वेव पैकेट है, it can represent an electron or a proton or even an alpha particle। At a t equal to 0, it is localized here। At a later time, one electron or one neutron or one proton is localized here as well as here। ये यहां भी है, यहां भी है। आप कहेंगे ये तो नहीं समझ में आया, वो क्या आधा आधा हो गया? नहीं, ये इट इज डिस्क्राइब्ड बाय ए वेव पैकेट विच इज हियर एज वेल एज देयर। लेकिन अगर आप मेजर करने जाएंगे तो इट कोलैप्सेस टू बीइंग हियर एज और हियर। मैं और एक और एक्सपेरिमेंट बताता हूं। देखिए, ये बीम स्प्लिटर एक्सपेरिमेंट एंड दिस इज ए सिंगल फोटोन सोर्स। मतलब ये लेजर लाइट है। आजकल ऐसे सिंगल फोटोन सोर्स कमर्शियली अवेलेबल है। तो इसमें से एक एक फोटोन निकलता है। तो मैं अगर कहूंगा कि मान लीजिए इसमें से 1000 फोटोन एक सेकंड में निकले, तो आप ये कहेंगे 500 इधर जाएंगे, 500 इधर जाएंगे एट रैंडम। दैट इज ए रॉन्ग आंसर। अगर आप ये कहेंगे कि approximately 500 will be reflected and 500 will be transmitted, that is a wrong answer. The correct answer is that a single photon source is described by a wave packet, and it will have a transmitted wave packet and a reflected wave packet. तो वो यहां भी है और यहां भी है। The photon is at both places. लेकिन अगर मैंने यहां पर डिटेक्टर लगाया और यहां पर भी, तो इट विल रिकॉर्ड द फोटोन आइदर हियर और देयर। इट विल कोलैप्स टू बीइंग हियर और हियर, नॉट एट बोथ प्लेसेस। तो आप कहेंगे आधा फोटोन इधर आ गया, आधा फोटोन आ गया, नहीं। ए सिंगल फोटोन is here as well as there, but when you make a measurement, it is either here or there. But these two parts of the photon can interfere with each other. This is the basic principle, basic concept of quantum mechanics, the superposition principle. देखिए, इस एक्सपेरिमेंट को देखिए। This is the single slit diffraction experiment जो आप ऑप्टिक्स में करते हैं। एक प्लेन वेव आया जो ऑप्टिक्स की किताब में है, and it's a slit of width b, long narrow slit of width b. It produces a diffraction pattern where the beta is equal to pi b sin theta. This is classical wave optics जो आप लोगों ने बीएससी में जरूर किया होगा। Now I solve the Schrodinger equation. I say at t equal to 0, the electron passes through this slit. So x comma 0 is 1 over root b for x less than, यहाँ पर origin है और बाकी जगह पर 0 है। This is a normalized wave function. अगर ये से psi of x0 से हम वो a of p कैलकुलेट करेंगे और a of p का mod square कैलकुलेट करेंगे। So the probability by passing, understand this, by confining the electron to pass through a slit of width b, the slit imparts a momentum. The slit है वो electron को momentum देती है, and the probability of the momentum lying between px and px plus dpx, if you calculate this, ये मैंने अभी जो 7th एडिशन है उसमें बहुत अच्छी तरह से कैलकुलेट किया है। वो किताब अभी तक आई नहीं है, आ जाएगी एक हफ्ते में। साइन स्क्वायर बीटा बाय बीटा स्क्वायर, और ये वही एक्सप्रेशन है जो यहाँ पर। एंड इफ यू कैलकुलेट इंटीग्रल पी ऑफ दिस थिंग, सो ये कहाँ जाएगी ये नहीं कह सकते। इसका एक प्रोबेबिलिटी डिस्ट्रीब्यूशन है, उसको क्वांटम मैकेनिक्स कैलकुलेट करती है। Before it hits the slit, it is described by a wave function which is everywhere. The process of measurement makes it collapse. कहाँ collapse करेगी आप नहीं कह सकते, You can only predict a probability distribution. चलिए एक और एक्सपेरिमेंट करते हैं. Double slit experiment, the famous double slit experiment. और जैसे आपने किया होगा, यहाँ पर एक सोर्स है, प्लेन वेव आ रहा है, यहाँ पर एक छोटा सा होल है या स्लिट है, and then you have two slits, and the intensity pattern is the multiple, the classical wave optics, single slit diffraction pattern multiplied by the 2 point in, and you see the interference pattern that I had talked about, the famous Young's double hole or double slit interference pattern. अगर आप Schrödinger equation को solve करना चाहते हैं, तो you start with a wave function at t equal to 0 as 1 over under root of p as sum. और इसको अगर आप वर्कआउट करते हैं, I leave it as an exercise. आपको अगर दिक्कत हो तो मेरे ऑप्टिक्स की किताब में है. So then the probability distribution is given by the same expression as this. This is a beautiful result. And so therefore, इसको बहुत ध्यान से सुनिए. This photograph is taken from the Feynman lectures. Now electron gun, इलेक्ट्रॉन जैसे वो बुलेट्स का एक्सपेरिमेंट किया था, इलेक्ट्रॉन को भी आप सोचते हैं कि एक इलेक्ट्रॉन गया, दूसरा इलेक्ट्रॉन गया, एक टाइनी पार्टिकल की तरह है. इट्स ए 2 slit और ए 2 hole एक्सपेरिमेंट. अगर होल नंबर 1 ओपन है, होल नंबर 2 क्लोज्ड है, इंटेंसिटी डिस्ट्रीब्यूशन ये है. अगर होल नंबर 2 ओपन है, तो इंटेंसिटी डिस्ट्रीब्यूशन ये है. अगर दोनों होल ओपन है, तो आप एक्सपेक्ट करेंगे कि इलेक्ट्रॉन आइदर पासेस थ्रू होल नंबर 1 और होल नंबर 2. इलेक्ट्रॉन आइदर स्लिट, फर्स्ट स्लिट से पास करेगी या दूसरे स्लिट से पास करेगी. सो द रिजल्टेंट मस्ट बी P1 plus P2. लेकिन जब आप एक्सपेरिमेंट करते हैं तो आप ये नहीं पाते हैं. What you measure is the interference pattern. और ये मान लीजिए सिंगल इलेक्ट्रॉन सोर्स है, एक इलेक्ट्रॉन गया, फिर उसके बाद दूसरा इलेक्ट्रॉन गया, फिर तीसरा इलेक्ट्रॉन गया. You observe the interference pattern. And therefore, to explain that interference pattern, we say that the electron, a single electron, one electron, passes through both the holes simultaneously. एक इलेक्ट्रॉन दोनों स्लिट के थ्रू कैसे जा सकती है? This no one understands. Not that I don't understand. No one understands. So the electron is described by a wave function which is present here as well as here. It interferes with itself to produce a probability distribution which is like this. And if you do the experiment, this is considered as the most beautiful experiment in physics. So it says the build-up of the electron interference pattern. तो अगर तुम्हारे पास 10 इलेक्ट्रॉन हो तो 10 स्पॉट्स आएंगे, 100 इलेक्ट्रॉन हो तो 100 स्पॉट्स आएंगे, और 70,000 होगा तो slowly the interference pattern will develop. What quantum mechanics tells us allows us to predict the probability distribution. And the probability distribution is the same as the intensity distribution predicted by the wave theory. So this is how the build-up takes place. और जब आपके पास millions of electrons होंगे, slowly the interference pattern builds up. You detect always one electron and never half of an electron, never half of a photon, never half of a proton, or never half of a neutron. You detect one electron or no electron. अगर आपने पता करने की कोशिश की, मान लीजिए यहाँ पर ये बहुत ब्यूटीफुली फाइनमैन लेक्चर्स में डिस्कस किया हुआ है, यहाँ पर एक लाइट सोर्स लगा कर कि कहाँ से इलेक्ट्रॉन गया, इस होल से या इस होल से. So if you इसको ध्यान से सुनिए. If you try to find out which hole the electron has passed through, then you will find it is either hole number 1 or hole number 2, not both holes. And the process of measurement will destroy the interference pattern. So this is a photograph of a young girl with 3,000 photons. There are 3,000 spots, and this is 28 million photons. तो आप ये कह सकते हैं कि the probability of the arrival of the photon here is very large. The probability of the photon arriving here is very small. एक photon कहाँ जाएगा? So classical physics is deterministic. This is the conceptual, and quantum physics is probabilistic in nature. This is tremendous difference. इसको लेकर आइंस्टाइन जिंदगी भर परेशान रहा. And he said, God does not play dice, but God does play dice. Quantum mechanics, which is now we will celebrate, I hope I live to celebrate in 2026, the 100 years of quantum mechanics, which is one of the most successful theories ever produced. So the most fundamental, David Bohm, who is considered as the best quantum physics, the most fundamental theory now available is probabilistic in form and not deterministic. So it's good that if you go to YouTube and write Feynman's messenger lectures, देखिए आप लोगों के पास अब टेक्नोलॉजी है. उस टेक्नोलॉजी, आई एम टॉकिंग टू द स्टूडेंट्स, उस टेक्नोलॉजी को आप कैसे यूज करते हैं? उस टेक्नोलॉजी से आप एक गंदी मूवी भी देख सकते हैं और दुनिया के सर्वश्रेष्ठ फिजिसिस्ट या साइंटिस्ट या मैथमेटिशियन या पॉलिटिशियन के लेक्चर्स भी सुन सकते हैं, गाना सुन सकते हैं. ये चॉइस अब आपके ऊपर है. So if you go to YouTube, you can listen to the most beautiful lectures by Richard Feynman, in which he says, ये उनके शब्द हैं. सुनिए, electrons do not behave just like particles. They do not behave like waves. जो मैंने कहा था ना कि electrons are neither particles nor waves. Electrons in orbits, जैसे hydrogen atom are not somewhat like a cloud. ये उन्हीं के शब्द हैं. Or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. You do not have a classical description of the electron. वो इलेक्ट्रॉन दोनों जगह पर कहाँ है, कैसे हो सकता है? एक फोटोन मिरर के इस तरफ भी है, इस तरफ भी है. वो कैसे हो सकता है? ये किसी को नहीं समझ में आता. And so therefore he says, there is one simplification. Electrons behave exactly the same way as photons. And then he says, I think I can safely say that nobody understands quantum mechanics. Why does he say that? He says that because how does the electron, which has a mass which is known, which has a charge which is well known, how does the electron pass through both the holes at the same time? That no one understands. चलिए इसको छोड़ दो. जैसे एक पोलराइड है, दिस इज अ सिंगल फोटोन सोर्स, इसमें एक्स पोलराइज्ड फोटोन आ गया और दो पोलराइड थीटा के एंगल पर है. The probability for the photon to pass through the second polaroid is cos square theta. And if the experiment is conducted with n photons, then about n cos square theta for. ये जो probabilistic concept है. देखिए मैं आपको एक सिंपल सा एक्सपेरिमेंट बताता हूँ. जैसे रेडियो एक्टिविटी है. मान लीजिए ये यूरेनियम का सैंपल है और इसका हाफ लाइफ मान लीजिए 1 दिन है. इसमें 10,000 एटम्स है. तो आप क्या कहेंगे? एक दिन में 5,000 एटम डिसइंटीग्रेट कर जाएंगे, उसके दूसरे दिन 2,500, उसके दूसरे दिन 1,250, समथिंग लाइक दैट, अप्रोक्सीमेट 1,240 भी हो सकता है, 1,260 भी हो सकता है. तो देखिए ऑल एटम्स आर आइडेंटिकल. some of them will decay in the next second. Some of them will live for 10 years. कौन सा एटम डिके करेगा कोई नहीं प्रेडिक्ट कर सकता. So quantum theory, in the phenomenon of radioactivity is embedded the basic concept of probability and therefore quantum theory. So Einstein said, for the rest of my life, I'll reflect on what light is. And then in 1951, he says, all the 50 years of conscious brooding have brought me no close to the answer to the question, what are light quanta? And he says, when he was 4 years before his death, of course, today every rascal thinks that he knows the answer, that is, he knows what light is, but he's cheating himself, he's deluding himself. So I am just an old storyteller. I do not know what the truth may be. I tell you, जैसे मुझे कहानी मुझे कहा गया उसी तरह से मैंने आपको कह दिया. This is, I tell you the tale as it was said to me. Sir Walter Scott. अच्छा डॉक्टर प्रजापति, मैं 4-5 स्लाइड और दिखाना चाहता हूँ. टाइम है?
Yes sir, sure sir. We can sit for full day, no problem.
नहीं, अरे मेरा गला सूख गया है.
नहीं सर, I can understand.
4-5 स्लाइड और दिखा देता हूँ. मेरा लेक्चर खत्म हो गया.
जरूर सर.
देखिए मैं आप लोगों को यंगर जनरेशन को कहना चाहता हूँ, because of the scientific base that has been created now. कभी टाइम मिलेगा तो मैं आपको history of development of science पर बताऊंगा. We have achieved a lot. We have achieved a lot. जैसे हमारा न्यूक्लियर एनर्जी प्रोग्राम है, which was established by होमी भाभा, राजा रमन्ना. आजकल हम एटम बम भी बना सकते हैं. इंडिया हैज ए फ्लरिशिंग एंड लार्जली इंडिजिनस, हमारा खुद का बनाया हुआ है, किसी ने मदद नहीं किया. न्यूक्लियर पावर प्रोग्राम. Then we have sent rockets in space. People like Abdul Kalam, Satish Dhawan, Vikram Sarabhai, great leaders, great scientists. और in 2017 में 104 सैटेलाइट में भेजे, एक वर्ल्ड रिकॉर्ड. It's a tremendous technological achievement. Then we had the Green Revolution, which was the father of Green Revolution is Swaminathan. Then we had the White Revolution. जब मैं अमेरिका से लौटा था 1964 में, तो दूध नहीं मिलता था. And one man, वर्गीस कुरियन, तो देखिए होमी जहांगीर भाभा was a Parsi, Jamshedji Tata was a Parsi, Verghese Kurian was a Christian, Swaminathan was a Hindu, Abdul Kalam was a Muslim. We are a diverse nation, and that is our greatest strength. That is our greatest beauty. That is why India is a great country. लेकिन आज अगर हम सोचते हैं, मैं बंगाली हूँ कि वेस्ट बंगाल सिर्फ बंगालियों के लिए है, महाराष्ट्र सिर्फ मराठियों के लिए है, तब ये देश टूट जाएगा. And then our target of installing solar power, ये हमारे प्रधानमंत्री का वो है. So we have achieved a lot. And he is soon going to have all villages lit up by solar energy. And then we have 1.2 billion mobile phones. आजकल फोन और इंटरनेट हर गांव में है. So we have achieved a lot. But then अभी भी स्लेवरी है. छत्तीसगढ़ में है, यूपी में है, बिहार में है, उड़ीसा में है. ये slavery in a brick manufacturing company. This photograph is in UP. अभी भी बहुत गरीबी है. अभी भी नेशन के राजधानी में, दिल्ली में 10 manual scavengers died in the sewers of Delhi. ये 2018 का तस्वीर है. अभी भी इतनी गरीबी है. अभी भी बच्चे इस तरह से पानी पीते. 30% of our population is below the poverty line. That is 400 million people are below the poverty line. इस poverty को कैसे हम लोग इस इतनी गरीबी से मुक्ति पा सकते हैं? It is only through education, science and technology. Only through education, science and technology. इसीलिए मैं, जैसे डॉक्टर प्रजापति हैं और भी हैं, उनकी मैं सराहना करता हूं, उनको मैं अप्रिशिएट करता हूं, इसलिए कि थ्रू दिस टेक्नोलॉजी आज हर एक के पास एक मोबाइल फोन है. तो एजुकेशन can only take us out from poverty, and we should use this technology to educate the masses. बाकी आप लोग तो सब समझदार हैं. So my unwanted advice to the younger generation is, have compassion, care and warmth. What is compassion? The dictionary meaning of the word is care and warmth for others. Visit your grandmother. Think of this old man pulling this heavy weight. If you want others to be happy, practice compassion. If you want to be happy, हम लोग क्या चाहते हैं कि हम लोग खुश हों. If you want to be happy, practice compassion. And the other thing to the younger generation is, have empathy. What is empathy? Make the effort to understand how others feel. Okay? So we live in difficult times. Right now in India, we are living in extremely difficult times. इतनी गरीबी है, उसके ऊपर कोरोना वायरस है. तो देखिए ना, कल परसों मैं टेलीविजन में देख रहा था, न्यूज चैनल में, एक कोई, आई एम ए हिंदू, एक कोई हिंदुओं का कोई मेला हो रहा था. तो उसमें एक राजनीति के, तो इतना भीड़ था. तो कहाँ सोशल डिस्टेंसिंग, कोई मास्क, सब लेडीज का भीड़ था. तो उससे तो कोरोना फैलेगा. कोई भी सरकार कुछ नहीं कर सकती. Unless we are educated, unless we realize our responsibilities, कैसे ये देश आगे निकलेगा? इस उम्र में आकर के मैं थोड़ा सा फ्रस्ट्रेटेड हूं. So we live in difficult situations. Human security are facing new challenges at the individual and global level. Education is the key dimension of the long-term process of building peace, tolerance towards religion, towards everything. I am a Hindu, but I must respect a Muslim. I must respect. आज जो ये टेक्नोलॉजी हुई है, it is because of Hindus and Muslims and Christians and Parsis and everything. The greatest scientist in our country, in my opinion, is Homi Bhabha, because he created this tremendous infrastructure. So we must have that tolerance, justice, and intercultural understanding. The reorientation of education to create a better world or a better country is truly urgent. This is not my quotation, but this is the Director General of UNESCO. तो बस यहीं पर मैं खत्म करना चाहता हूँ. मेरा गला भी बिल्कुल सूख गया है. Thank you, Dr. Prajapati, for giving me this opportunity. लेकिन ये आपके वेबिनार का तो ये है ना कि पता नहीं चलता है कि बच्चे सो गए या भाग गए. चलो.
Sir, thank you very much, sir. Sir, we have few questions from students, and before that, I would like to invite HOD of our department, Pure and Applied Physics, Professor P.K. Bajpayee, because somehow he could not join at the starting of this webinar. So Professor P.K. Bajpayee sir, please. Sir, your audio is mute, sir. Okay, I have done it.
On behalf of the Department of Pure and Applied Physics, it's a real delight for me to welcome formally Professor Ghatak. It was indeed a real academic feast. I was unlucky not to join because of some other program I had from 9:30 to 10:30. I was 2-3 minutes late, and I apologize for that. Traversing through the history of science, covering almost 350 years, in a very smooth manner was possible only by a teacher like Professor Ajoy Ghatak. We all have been the students of science, evolving ourselves, going through the books written by Professor Ghatak, be it optics, optoelectronics, lasers, quantum mechanics, and so on. Listening from the horse's mouth, and in such a simplistic manner, covering not only the most difficult transformation from classical physics to the idea of quantum mechanics, it was not possible in one lecture for anyone. We all have been familiar with the Feynman lectures, and the whole world understand the most stimulating lectures given by the teacher of physics. But today's lecture, in my opinion, had all the nitty-gritty of quantum mechanics, including the perceived reality due to the measurement, including the nature of light as well as the nature of electrons, neither a wave nor a particle, what it is, the mathematical construction of wave function, up to the synthesis of optics, electricity, magnetism, and the most important sentence which I consider, which I have learned today, that the laws of physics cannot be derived. They are understood, they are created in the minds of genius, like he himself has quoted, be it Einstein, be it Schrodinger or Heisenberg. And this takes us at the ontological level, at epistemological level, what is reality? And this is why the quantum mechanics becomes the best science produced so far. And this science has been explored and exposed to us today by Professor Ghatak. On behalf of this department, on all our behalf, we heartily grateful to Professor Ghatak, and I'm sure that we have been making this program in the department, Professor Ghatak, for last 1 year to invite you and have the nitty-gritty of science learn from you. However, due to some reason or other, we could not come face to face, but I'm sure that in coming times, you will have time for this department to come, and we will have the opportunity to meet you face to face.
Yes.
But I'm also grateful to Dr. Prajapati, who initiated this webinar series. And today we have a lecture from the dawn of science, I would say, in our era, Professor Ghatak. I heard him many times, but most of us, I'm sure, had the first opportunity of understanding the way physics should be understood. We have been studying his books, but understanding the science and the interpretation of science, especially that of quantum mechanical concepts, it gives very, very difficulty in the classroom to make the student understanding without losing the rigor of mathematics involved. This is one of the most difficult thing in teaching quantum mechanics. I myself have been teaching quantum mechanics from last 30 years or so. But I have learned a lot today.
Really?
Frankly speaking, sir, it will be a nice idea if you can spare time to give some more lectures, especially as you have said, the mathematical part of quantum mechanics, understanding the concept of wave function, how the wave function collapses with the measurement, how the Fourier transforms are utilized in quantum mechanics, and even more in the field theories and relativistic quantum mechanics. These ideas becomes more and more rigor and at conceptual level very difficult to understand. Mm, Traversing with you from general optics to wave optics to the idea of wave, and then making the light wave as the electromagnetic wave, and highlighting the Maxwell equations and the displacement current idea. I can't say I will repeat the whole lecture, but it's really a delight. I find the words not coming appropriately in describing the lecture. The interpretational questions about quantum mechanics without exceeding the mathematical rigor that it requires, excellence. We are really grateful, and I know after listening such a great lecture, nobody would like to listen me, but it's my moral duty to give a very brief idea of our department. This
Certainly.
department was established, sir, in 1995. We two, myself and Dr. Tiwari, we joined the department as the first permanent faculty in 1996. And we offer programs at PG level and UG level in physics and electronics. And in physics, we are having a specialization in experimental and theoretical condensed matter physics, laser physics, plasma physics, nuclear physics, astronomy. In electronics, we are focused on communication electronics. And at UG level also, we are running the CBCS-based BSc program, honors in physics and electronics. We are also taking care of BTech students of our Institute of Technology. And during these 24, 25 years, we have been able to attract very good faculty. One of the basic strengths that our department has,
That's
we
very
have faculty from Pan India, from South, from Bengal, from Madhya Pradesh, and all our faculty members, fortunately, I'm lucky that they are well trained in almost very good institutes all over the world, from US, from South Korea, from Germany, from Israel. And we have developed, fortunately, fairly good experimental facility, as well as the DFT-based theoretical laboratories. In addition to this, sir, we are probably the first university in India to have a full-fledged accelerator program. We have a
very
3 megavolt, 3 million volt Pelletron accelerator, a low energy accelerator that we plan to generate neutrons in near future, where we will be having the experiments for the neutron activation and for accelerator driven reactors simulation experiments. At present, of course, these accelerators we have been using for the material characterization and material modification. The two beam lines that we have, it produces ions, energetic ions up to almost 40 MeV. Almost all ions of periodic table up to uranium, including the protons and alpha. And unfortunately, this accelerator program is now non-functional from last 1.5 years or so because of certain technical reasons. But fortunately, the UGC has taken up to consider it as a national center, and we are going to have a MOU with the UGC and Inter-University Accelerator Center. So this becomes a joint center of university and IUAC, having funding directly from UGC. So in very near future, we are hopeful of again starting the experiments. And in addition to this, we have fairly good facilities in the field of condensed matter physics, material science, nanotechnology, and in the field of electronics, especially in making the devices. With this,
very nice.
So I wish that sometime you physically visit our department, interact with the faculty and students, and this will be a very motivating and very inspiring moment for our department, and your expertise, the teacher within you that we have seen today, the way you were explaining, that teacher we want to use as our mentor. And I'm really grateful to you as well as to Dr. Prajapati for providing this moment, this opportunity of listening a high-class lecture from a real physicist. Thank you very much.
Thank you. Thank you. I have, thank you very much for your very nice thing. There was a from Jitendra Singh. Can we consider the existence of God as a practical application of quantum mechanics? Let me tell you something. If you listen to those Feynman lectures, you know, I did my PhD from Cornell, and one of my greatest regret was I could not listen to the Feynman lectures because they happened after I left. But now with technology, we can listen to the Feynman lectures. So you see, it is as good or better because we can listen to that again and again and again. So उस एक Feynman lecture में, this beautiful lecture on gravitation, and Feynman says, और मैं आप सब सुनिएगा उसको, आप लोगों ने शायद बहुतों ने सुना भी होगा, that motion of planets cannot determine the future. The astrology, he says, ये जो किसी ने सवाल पूछा ना, God of course exists. We all are. अरे इसका रिकॉर्डिंग बंद कर दीजिए. तो गॉड तो है ही, लेकिन जो आप, हाँ, इसका रिकॉर्डिंग जरूर बंद. डॉक्टर प्रजापति, तो मैं ये कहना चाहता हूँ यंगर जनरेशन को, देखिए ना, टीवी चैनल देखिए, हर टीवी चैनल, बंगाली टीवी चैनल हो, उड़िया चैनल हो, हर जगह पर आजकल वो नक्षत्रों के पोजीशन से आपके फ्यूचर को बताना, ये सब हम लोग सो कॉल्ड एजुकेटेड पीपल सुनते हैं, ये तो सारा गोलमाल है. सो ये गॉड मैन, I believe in God, but I do not believe in God man. I do not believe in astrology. एक अंगूठी पहन करके कुछ नहीं हासिल हो सकता, कुछ नहीं हासिल हो सकता. So the younger generation should realize that. तो जितना भी मैं देखता हूँ, और मैं दूसरा चीज ये कहना चाहता हूँ कि आपने जो कहा, आप लोग इतना कोशिश कर रहे हैं टू ब्रिंग अप द डिपार्टमेंट, टू मेक इट ए सेंटर ऑफ एक्सीलेंस, इसको सुनकर मुझे बहुत खुशी हुई, क्योंकि द यंगर जनरेशन टुडे, द ब्राइटेस्ट ऑफ द ब्राइटेस्ट, वो बस किसी तरह से डिग्री लेकर के एमबीए करना चाहती है. बेसिक साइंस या बेसिक मैथमेटिक्स या बेसिक केमिस्ट्री पे ज्यादा ध्यान नहीं. ये बहुत बहुत चिंता का विषय है, क्योंकि हमारे देश में टेक्नोलॉजी लाने के लिए अच्छे बच्चों को जो पढ़ाई लिखाई में सीरियस है, उनको साबुन बेचने की जगह they must be doing research, and I'm so glad you are putting in so much of an effort in creating infrastructure facilities in Bilaspur and in other places. Many people are trying. I hope that takes away, even in IITs, आप देखेंगे अच्छे बच्चे सब MBA करके कुछ भी करना चाहते हैं. Money is important, but we, the older people, also have the responsibility of creating infrastructure, जैसे आप लोग कर रहे हैं, of creating better facilities, better environment. And I'm so glad that you have collected people from all over the country to be in your place. So I'm really very, very happy to participate in this program, to be with you all. And my perception of God, quantum mechanics, you see, quantum mechanics जो भी बहुत गंभीरता से पढ़ता है, वो चाहे श्रोडिंजर हो, चाहे डेविड बोम हो, वो सब फिलोसोफर बन जाते हैं, इंक्लूडिंग माय ओन गुरु प्रोफेसर DS कोठारी. लेकिन मैंने उतना दूर तक नहीं पढ़ा है. बट ये जरूर है कि सुपरस्टिशन को हमारे दिल से निकाल लेना. That is for sure. That is for sure. So Einstein said, I will quote Einstein. Einstein said, that, do you believe in God? And listen to this carefully. He said, I believe in a creator, but I do not believe, I do not believe in a God of theology which rewards the good and punishes the evil. I do not believe in a God of theology which rewards the good and punishes the evil. And he also said that the biblical stories that they were taught, they could not be true. They were not true. And we must be scientific in our approach. Believe in the existence of a superpower who has created us. When we look at our beautiful eyes, hands, life, reproduction, we feel that there must be a greater superpower. Of course there is. But to think, to believe unconditionally something, that उस बृहस्पतिवार के वजह से आज हमारा परीक्षा में रिजल्ट ठीक नहीं होगा, that is not possible. तो ये तो endless discussion है. Thank you so much, Dr. Prajapati. Congratulations to all of you for organizing this event. I hope it was worth it. चलो मैंने तो अपनी तरफ से पूरी कोशिश की थी. Thank you so much.
Sir, there are 1-2 questions. If you answer, so I picked them there. So there is one question from Dr. Puni Prasann Paltani from IIT NER Raipur, that can you prove the special theory of relativity using quantum mechanics?
तुम्हारा वॉइस नहीं ठीक आ रहा है, ठीक नहीं आ रहा है.
Sir,
हाँ,
question
बोलो.
from P. Paltani is that can we prove special theory of relativity using quantum mechanics?
I couldn't follow. But relativity, of course, you have the relativistic quantum mechanics introduced by Dirac and the Klein-Gordon equation. The Schrodinger equation is non-relativistic. E is equal to P square by 2m plus V of R. The Klein-Gordon equation is relativistic in nature. But the Schrodinger equation that I wrote down is non-relativistic equation. And then for the electron, we have the famous Dirac equation. The Dirac equation predicted the magnetic moment of the electron, but then it required the quantum field theory, and even for proton, you cannot use the Dirac equation. So there is something beyond that. But having said that, all atoms and molecules, the entire field of chemistry, can be understood by solving the Schrodinger equation. Entire chemistry, a large portion of solid state physics, nuclear physics, can be understood by solving the Schrodinger equation. You write down the Hamiltonian, you write down the Schrodinger equation, and you just solve it, and you will get the solutions which are valid to 10 decimal places. So it has worked in many cases, but there are certain regions where it has to be supplemented by the field theory. But quantum mechanics as such, that's what people say, that it has withstood the test of time. It has been there for now 100 years. Quantum mechanics, the Schrodinger equation and the quantum mechanics itself was discovered in 1926. And I hope 2026 we will celebrate the centenary of quantum mechanics. And so it has withstood for 100 years. And I hope that it can withstand for another 100 years. चलो खत्म करते, मेरा गला भी बहुत सूख गया।
हाँ, thank you very much sir. Just मैं conclude करता हूँ. So I am thankful to the respected professors, faculty members, scientists, research scholars, and students who have participated in this webinar. And especially I am thankful to Professor Ajoy Ghatak for giving us some time and giving this webinar on the famous topic evolution of quantum theory. Professor Ghatak is very generous and great human being. His simplicity is, I think, more than the toughness of the quantum mechanics. So let's thank to the speaker of today's webinar, Professor Ghatak sir, and I hope that he will be continued in our future webinars also. So thank you again, sir. Thank you very much.
Thank you. Thank you.
So let us end the meeting. Okay.
Thank you.